We're going to look at a number of very powerful and practical applications of eigenvalues in the last episode. But what I want to do in this segment is talk a little bit more about the theory of how eigenvalues and eigenvectors really do represent the innards and the structure of a matrix in a way that lays its action bare. And we're going to use a linear algebra concept called a basis, which I've only hinted at until now. It's actually pretty important, but I think you'll pick it right up. We're going to talk about the basis for a set of vectors and how the eigen basis of a matrix is actually in some sense the most natural basis to use. All right, so we're going to talk about that. Before we do that though, let me make a different point. And I want to talk about multiplication of matrices when we multiply by a diagonal matrix. And I just want to make a certain point about this, and it may not make sense right away, but you'll see by the end of this segment why it's important. So suppose I have a 3 by 3 matrix. I'm just going to say 3, 1, 5, -2, -4, -6, 9, 9, 9, something like that, right? Now, if I multiply this by a plain old 3 by 3, say, 1, 9, 7, 6, 8, 2, 4, 5, 3, if I asked you to carry out this multiplication manually, you would probably cry, right? Because there's a lot of calculation to do here. We have to do a lot of dot products. We've got to do that thing, dot product it with that thing, which involves 3 separate multiplications and the addition, all making sure you don't make any goofs. And all that ends up giving you is what's in the upper left-hand corner of your result. Then you got to repeat that 9 times in order to get all of the different values here, okay? So that's matrix multiplication. We know how to do that. I want to draw your attention, though, to the fact that it's a little bit easier, in fact, it's actually a lot easier, if this is a diagonal matrix here, okay? So let's say this matrix was really 2, 4, 1, and all the rest were zeros. Now, at first blush, this is still the same difficulty, right? You've still got the same number of operations to do. But you'll start to realize how much easier this is, especially when you think about the version of matrix multiplication we talked about, which is linear combinations of the columns, okay? So you'll remember that really this matrix is composed of 3 columns. And when we look here at this first column, really what we're saying is, in my final result, I want to have this many of the first column plus this many of the second column, plus this many of the third column, right? No matter what entries are in here. And if 2 of these entries are 0, well then, wow, that's actually really easy, right? Because all it is double that guy. We're saying that what we want in our left column of the answer is 2 of the A column, none of the B column, none of the C column. So that's something that if you have your wits about you, you can just do in your head, right? You could say, well, that's going to be 6, 2, 10. I just doubled the left column. And then this one here is 0, 4, 0. So that basically is saying, I don't want any of A, I don't want any of C, and I want 4 times B. So that's going to be, if my math is correct, -8, -16, -24. And then the final column says, I want none of A, none of B, and 1 of C. So that's going to end up giving us a 9, 9, 9. Okay? So my first point is that if this matrix is diagonal, number 1, it is an easy operation to do. It's trivial. You can do it in your head practically, rather than doing all those laborious multiplications and additions 9 different times. Second thing is that really it's not only easier to calculate, but what you're really doing is saying these 3 vectors, I simply want to take some amount of each one of them separately for our final answer. Okay, so file that fact away just for a moment, and we're going to come back to it, and you'll see why this matters. Multiplying by a diagonal matrix is significantly easier and also more understandable than multiplying by just a general matrix. Okay, all right, so now let's talk about a basis. A basis, you'll understand this right away now that you understand about blue and yellow vectors. Okay, a lot of the linear algebra books I've read have really a kind of a complicated definition of basis, but it's really very simple. Basically, a basis is simply the following thing. A basis is any full but not overfull, you'll see what I mean in a second, set of yellow dominoes. That's it. Remember, yellow dominoes are linearly independent and they don't behave badly. They are separate from each other, and each one of us gives the ability to traverse our space in a new direction. Okay, so let's say we're dealing in 2 dimensions here for a second, right? So we're dealing with a plane. This is real easy to visualize. We've got our x and y axes here, okay? So if I say I'm going to give you the domino 1, 0, and I'm also going to give you the domino 0, 1, my question is, using only those 2 dominoes, can you get to any place on the plane? And the answer is obviously yes, right? Let's say I wanted to get to the point 1, 7. Okay, so this is 1 in this direction and 7 in this direction, right? Can I get to that place going only in these 2 directions? Well, obviously yes, right? I take 1 of this first guy, and I take 7 of this second guy, and I add those together, and I, in fact, get that vector that's pointing right to that space, okay? Now, when I say full, what I mean is it has to be the size of the space. If we're dealing with a 2-dimensional space, we're going to need 2 vectors in our basis. Otherwise, it's hopeless. You can't get everywhere, right? But if I give you any 2 dominoes, as long as they're yellow, you can get everywhere, right? We've seen that a lot. Now, of course, if I give you any other domino also, right? Like if I tried to sneak in here, oh, I'm also going to give you 5, 4. You're going to cry foul and say, oh, that's over full now. Right? Because you don't need to give me 5, 4. I can already get to 5, 4 all on my own, thank you, by using 1, 0 and 0, 1. So this here would make this set of vectors not a basis because now it would be over full. So a basis basically allows you to get everywhere, and it allows you to get everywhere in only one way. That's the thing that turns out to be important about it, right? If we actually had all 3 of these at our disposal, then there'd be a crazy number of different ways we could get to the point 1, 7. And the nice thing about a basis is that every point is reachable in exactly one way, okay? Now, up to now, this basis right here, which by the way has a special name, this basis is called the standard basis. It is the basis which consists of vectors which are all zeros except a 1 at each position, right? So if we're dealing with 2 dimensions, these are the 2 vectors in the standard basis. If we were dealing in 4 dimensions, we'd have 1, 0, 0, 0. We'd have 0, 1, 0, 0. We'd have 0, 0, 1, 0. And we'd have 0, 0, 0, 1, right? That would be the standard basis in 4 directions, okay? Now, it's called standard partially because you're like, well, that's the first thing you'd think of. Boy, this eraser really sucks. I have to push really hard to get this stuff erased. One of the reasons that it's standard is because it's kind of the first thing you'd think of, right? But what I want you to see now is that this is not our only choice of basis. When we say we're dealing with the point 1, 7, we could, in fact, say that is 1 of the 1, 0 domino plus 7 of the 0, 1 domino. But I'm going to give you another basis here. I'm going to give you a basis 2, -3, and 5, 1. Okay? I'm going to call this the wacky basis. It's wacky just because I kind of randomly just pulled these numbers out of a hat. Okay? Now, we know from earlier episodes of this volume of All the Math that as long as these 2 vectors are yellow with respect to each other, and I assure you they are, if you want to graph them, you can easily see they're not on top of the same line, which is the only way to get blue ones. As long as these are yellow, we can, in fact, get to every point on the plane. We can get to 1, 7 just as easily as we did here, okay? You might ask, how do we get to 1, 7? Well, I worked it out, and it turns out in this case, it's -2 of this wacky basis vector, and then we're going to say add 1 of the 5, 1 vector. And if you do the math here, I think you'll realize that this is -4, 6, and if you add -4, 6 to 5, 1, you're going to get 1, 7, right? So here what I did was I said, I have a vector that goes in the 2, -3 direction. That's my first wacky basis vector. And I said, let's go -2 times this vector, which of course is going to put us this way, and it's going to be twice as long. And then I said, add 1 of the 5, 1 vector, and that's going to take us over 5 and up 1, and we're going to get to exactly the same spot. Okay? So the bottom line is that this point here, even though we might think of it as this is kind of the real way to represent it, It really isn't the real way. It's just the standard way. And by the way, the standard basis is often called B sub S. That doesn't stand for any curse word. It stands for basis, comma, standard. And I'm going to call this one down here basis, comma, wacky. Okay? So one way to represent this point here is to say this is the point 1, 7 sub BS. That means using the standard basis, we have 1 of the first vector in that basis plus 7 of the other vector in that basis. This, however, is equal to negative 2, 1 in the wacky basis. Whoa, how did I get that? Well, I got that here. We wanted negative 2 of that guy and 1 of that guy. Those are exactly the numbers I've got here. Okay? So take a second and look at this. 1, 7 is only the correct representation of this point if we're using the standard basis. If we're using any other basis, then it would be a different number of elements here. Okay? And again, this is true for every point on the plane. Let me give you just one more, just kind of for completeness here. So another one that I worked out was the point 7, negative 2. So if we go over 1, 2, 3, 4, 5, 6, 7, down 2, right there, that point right there. Okay? Can I get there in the standard basis? Obviously, yes. I would take 7 of the 1, 0 vector, and I would subtract 2 of the 0, 1 vector. Bada boom, I've got 7, negative 2. And if I wanted to use the wacky basis, it actually would be a little bit easier because it turns out to be just 1 of each. 1 of the 2, negative 3, plus 1 of the 5, 1. You can easily realize that that's 2 plus 5 is 7, negative 3 plus 1 is negative 2. And so if I go 1 in this direction here, and then I go 1 in this direction here, we do in fact get to the same point, 7, comma 2, so, comma, negative 2, right? So again, we end up with the fact, bigger bracket here, we end up with the fact that 7, comma, negative 2 in the standard basis is the same as 1, 1 in the wacky basis. Okay? Now, why does this matter? It matters for a lot of applications where we want to do a so-called change of basis. And there are times where if you express the vectors in one basis instead of another, certain operations end up being simplified and you end up getting rid of a lot of terms and stuff. And that's certainly what we're going to see with these eigenvectors here, okay? There is something called a change of basis matrix, which is usually called COB, change of basis matrix. And let me just show you what that looks like. So if I want to do the change of basis matrix to the standard basis, so let's say I want to do the change from the wacky basis to the standard basis, the change of basis matrix that I multiply by is really easy. It is simply my wacky vectors right next to each other. 2, negative 3, 5, 1. You'll remember on the previous slide, those were our wacky vectors. So this right here is the COB from B wacky to BS. There's a lot of, subscripts there. But that's what this is. So let's just see if this works, right? What happens if I take 2, negative 3, 5, 1? So one of our examples was we had 1, 7 in the standard basis was equal to the negative 2, 1 in the wacky basis, right? So let's make sure our change of basis matrix works as advertised. Let me take a wacky basis vector, which is negative 2, 1, and let's multiply it by this change of basis thing. So we get 2 times negative 2 is negative 4, plus 5 times 1 is 5. That gives us 1. And then negative 3 times negative 2 is 6, plus 1 is 7. 1, 7, bada boom, bada boom. So we feed in a vector in the wacky coordinates, and we get out the equivalent vector in the standard basis coordinates. Okay? So this matrix here converts from the wacky basis to the standard basis. Now, what if I want to go the other way? What if I want to convert from the standard basis to the wacky basis? You may realize how to do that. What you do is you take the inverse. So the change of basis matrix going from standard to wacky is equal to the change of basis matrix going from wacky to standard inverse. How do you figure out the inverse? You ask Python. So I asked Python, I said, hey Python, what's the inverse of this matrix right here? And Python said, well, I'll let you in on a secret. It is 0.059, 0.176, obviously I'm rounding here, 0.294, and 0.118. And we learned how to do that in Python and in R in the previous episode, right? So if I take this thing right here, and I multiply it by, kind of running out of room, but let's say I multiplied that by 1/7. I won't work it out because there's a lot of decimal numbers, but if you do that, I assure you, you will get -2,1, okay? So bottom line, this matrix and its inverse here allow us to freely go back and forth between the two bases, okay? And you can always change basis from any basis to any other basis simply by multiplying by a change of basis metrics, right? Now, we're doing all this in 2 dimensions. You could, of course, do it in 3 dimensions or 12 or 100, right? All the principles are the same. You just have to have 100 basis vectors in one of your bases, and then another 100 vectors in your other basis for your 100-dimensional space, and all 100 would have to be linearly independent of all the combinations of all the other ones, etc., etc. Then you multiply by your 100 by 100 thing, and then you get your change of basis. Okay? All right. Now, what does this all have to do with eigenvalues? Well, here's what. Remember that the spectral theorem, the all-important spectral theorem, says any square matrix M, as long as it's not one of the weird ones, every square matrix M can be expressed this way. This is the eigenvectors. This is a diagonal matrix of the eigenvalues. And then this is the inverse matrix of the eigenvectors. Okay? Now, here's the thing to get your head around. Let's go back to our original matrix we've been using kind of an example here, right? So we used this one, which was 1.5 and -0.5 and -1, right? So that matrix equals its eigenvectors times the matrix of an eigenvalues times the inverse of its eigenvectors, right? Now, the eigenvectors, you'll remember, were 1 and -1/2 was one of them, and that one had a lambda of 2. And then the other one was 4, 4, and that had a lambda of 1/2, right? Now, one thing I want to point out here is that, remember, any vector in this direction is an eigenvector with that eigenvalue. It doesn't have to be 4, 4. It could be 2, 2, 8, 8, 100, 100, etc. All of those point in the extreme northeast to southwest direction. Therefore, they are all eigenvectors, right? And this one here, anything that points in this exact direction also is an eigenvector. So what we typically do here is when we put the eigenvectors in, we put them in normalized. In other words, we put them in with a norm of 1. So when I write these numbers, it'll seem weird at first, but don't let it be too weird because all I've done is normalize it. -0.894 rather, and 0.447. This right here, if you figure out the Euclidean norm, right, if you take the square root of 0.984 squared plus 0.447 squared, it's going to be equal to 1. Great, so this vector here has length 1. And if you figure out what direction it's pointing in, you'll realize, it's pointing in exactly the 1, -1/2 direction. And then over here, I'm going to put 0.707, 0.707. This one also adds up to 1, or not adds up, but the length of this is 1, the length of this column is 1, and it points exactly in the 4, 4 direction. Okay? So these are the eigenvectors, even though they don't look exactly like this, simply because I've scaled them to be normalized. Then this thing here is going to be 2, 0, 0, 1/2, right? Because we've got the eigenvalue there of the first eigenvector, we've got the eigenvalue there of the second eigenvector. And then this here is the same as this guy, but inversed, right? So I asked Python, I said, hey Python, what is this inverse? And Python said, hey, I'm glad you asked. It's this, 0.746 negative, 0.471, 0.746 positive, 0.943. Okay? Now, I know it's a bunch of numbers you're looking at. And you're like, okay, why is this important? So here's the thing. If you look at this, you will realize, holy moly, this is the change of basis matrix from the standard basis to the Eigen Basis. What's the Eigen Basis? The Eigen Basis is the basis with the eigenvectors in it. So any two yellow dominoes form a basis. You could take 1, 1, and 2, 3. You could take 1, 0, and 0, 1. You could take 19, 5, and negative 4, 7, right? Any two pair of yellow dominoes works. You could also take the eigenvectors. And what we're going to do right now is take the eigenvectors here, okay? So that rightmost matrix is the change of basis from the standard basis to the eigenbasis. What is this guy here? This is the change of basis matrix from the eigenvector space into the standard basis. And what is this? This is just a scaling operation. As I mentioned at the beginning of this segment, all this thing does is take twice the first column instead of just having the first column. It doubles it. And it takes half the second column instead of just taking the second column. It takes half of it. Right? Multiplying by a diagonal matrix is very easy, and it's very easy to interpret because all it does is scale each of its columns by a certain fixed amount. Okay, so what I want you to see here is this assembly line. Here's what happens when we feed in some vector that we want to transform with this matrix. Let's say we fill in, 315 or something. I want to pump this through this matrix and see what comes out. I want to see what m times 315 is. There's two ways to do it. One way is to do all this crazy math with all of these cross products and blah, 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 and come up with the answer. Okay, that's totally fine. But I want you to see the beauty here, because here's the other way to do it. We could take this vector here, which of course is expressed in standard coordinates. When we say 315, what we mean is 3 in the x direction and 15 in the y direction. When we take this thing and multiply it by this guy, all that does is take the same vector, but express it in eigencoordinates instead of standard coordinates. It's the same vector. We've just transformed it to eigenland. It's now in the eigenspace. Now that it's in the eigenspace, all we do is say, well, this eigenvector is 4 times as important as this one, because this one, you multiply it by 2. This one, you only multiply it by 1/2. That's what gives it its oomph in the first eigenvector's direction, the dominant eigenvector's direction. So once you've got it in eigenspace, there isn't any computation to do except just scaling each of the eigenvectors. And then once you've done that, what do? Well, you just convert it back to the standard basis, and that gives you your answer. So this is why the eigenbasis is considered the most natural basis to express vectors in. Any other basis, even the standard one, comes up with crazy math that just kind of looks like it's just a bunch of random stuff multiplied by each other. But if you realize that the function of the matrix is to increase or decrease incoming vectors in the eigendirections, then you'll realize, wow, that's pretty neat. All I gotta do is turn it into eigenspace, and then there isn't any math to do except just shrinking or growing along each of those dimensions. And again, the power that each one of those eigenvectors has is related to its eigenvalue. If it has a really high eigenvalue, that means that stuff that's in that direction in eigenspace is gonna get way blown up. And if it has a small eigenvector, that means stuff that's in that direction in eigenspace is gonna be really shrunk. And that's going to have really important ramifications when we talk about video compression in the next episode, because we're going to talk about how you can get an approximation to a video picture, say, instead of getting the whole thing in far less data than it would take to transmit the entire thing high res, simply by using a subset of the eigenvectors, only the ones that have high eigenvalues. Whew! Kind of blows your mind.